A cube is a study in uniformity. Every face is identical, every edge is equal, and every corner locks into a perfect right angle. Because of its flat faces and square corners, the geometry feels completely settled. It is a rigid, predictable box that seems to offer no room for structural surprises. Yet hidden inside this grid is a highly specific, irregular decimal angle of precisely 54.74 degrees. This is what scientists call the magic angle. It is a precise metric used to calibrate multi-million-dollar scientific equipment across chemistry and physics. To understand how a decimal like this powers modern science, we have to look past the square faces and find where it hides inside the volume. We can find this angle by building the cube's dimensions one step at a time. We'll start with the simplest unit, a single edge with a length of 1. In 2 dimensions, we can draw a face diagonal straight across one of the square sides. Using basic trigonometry, we know the length of this flat diagonal is exactly the square root of 2. Now we move into the 3rd dimension by drawing a space diagonal, a line cutting through the interior of the cube from one corner to the opposite corner. Because this line travels across 3 dimensions of length 1, its total length is the square root of 3. At the intersection, where the edge meets the space diagonal, the math reveals something specific. The cosine of this angle is 1 over the square root of 3, which calculates to 54.74 degrees. Because a cube is perfectly symmetrical, this exact 54.74 degree angle forms between the space diagonal and all 6 edges that meet at its endpoints. There is a common spatial trap here. If you measure the angle between the space diagonal and the flat face diagonal, you won't find the magic angle. That intersection creates a smaller 35.26 degree angle. Together, these 2 internal measurements add up to exactly 90 degrees. We can also find this angle from the outside. In this diagram, a cube is sliced through the midpoints of 6 edges. This cross-section creates a perfectly regular hexagon inside. The dihedral angle between this tilted slice and the flat base is exactly 54.74 degrees. Whether we measure intersecting internal lines or tilted slicing planes, the magic angle is a structural property woven into the shape itself. The magic of this angle comes down to a single mathematical result. At 54.74 degrees, the cosine squared of the angle is exactly 1/3. This specific fraction allows scientists to zero out a complex physics expression, 3 cosine squared theta minus 1. In physics, that expression describes orientation-dependent static. It is the magnetic noise that often makes it impossible to get a clear scan of solid materials. To solve this, machines like this nuclear magnetic resonance scanner spin solid samples at precisely 54.74 degrees. By aligning the sample to this angle, scientists force the magnetic interference to drop to 0, leaving behind a clear, readable signal of the atomic structure. The cube serves as a rigorous physical model for interpreting 3-dimensional direction and symmetry. Even the hyper-advanced engineering of an NMR machine relies on the same basic geometry taught in a high school classroom. These multi-million-dollar instruments are calibrated using a property that was already present inside a simple block. The magic angle shows that even our most complex observations of the atomic world can be simplified by the inherent symmetry of the cube.